All right. Good afternoon, everyone. Let's take a look at any questions that you might have from the lesson way back on Wednesday dealing with one-sided limits. Briefly, this was a bit of a stopover on the way to bigger and better things. You are going to need to know how to deal with one-sided limits later on, in particular when we go through a couple of what we call theorems or proofs. The concept of a one-sided limit is very important. You also need to know that one-sided limits are crucial in understanding continuity. Specifically, if the limit as x is approaching some value of a function happens to be equal to the value of the function at that point, then you're saying a number of things. One of the things you're saying is if you're saying the limit is equal to something, you're saying the limit exists. And that means if the limit exists, then the left-handed limit and the right-handed limit must be equal to each other. The left and the right-hand limits being equal to each other doesn't guarantee that the limit exists. For example, when you take a look at question 1, sorry, let me get my bearings here. E and F lead up to G. Looking at the graph, as x approaches 2 from the left, what does the function approach? The function approaches 3. Right, as you're getting closer and closer to x equals 2 from this side, you're getting closer and closer to y equals 3. On the other hand, when you approach x equals 2 from the other side, the function is also getting closer to 3, which means since the left and right hand limits are equal, then the entire limit exists and happens to be equal to 3. But looking at the graph, it's clearly not continuous there, because 3 is not f of 2. And most of the time, you see situations where f of 2, as an illustration, doesn't even exist because there's nothing there, right? But sometimes f of 2 does in fact exist. And in this case, in this function, and I'm referring to this, f of 2 happens to be equal to 2. Right? When x is 2, y is 2. But when x approaches 2, y doesn't approach 2. So the limit exists in G, but the function is not continuous because the limit is not equal to the y coordinate at 2. I think that does it for kind of a quick review here. Does anybody have any questions you would like me to go over from this section? Yeah.
For H, I, and J.
For H, I, and J. And they are all connected to each other. I'm going to analyze the function f of x equals the absolute value of x over x. Okay, and what I'm going to do here, Fazile, is I'm going to write it into two pieces. And this is what you do whenever you encounter an absolute value function as part of the operation in calculus. You say to yourself, well, the absolute value of x over x is equal to x over x if x is greater than or equal to 0. And I want to highlight some stuff here. I'm talking about this x being this x. Okay, I'm saying if x that's in the absolute value, which is the same as the x on the bottom, but I'm talking about that one. If x that's in the absolute value is already greater than or equal to 0, then we don't need the absolute value signs. That's a fact. Does that make sense to you? Okay. On the other hand, if that x is less than 0, then we can drop the absolute value signs, but then we will be left with a negative quantity. And absolute value means we want the positive quantity. So that means if what I've highlighted is negative, applying the absolute value to a negative involves multiplying the argument by -1. And we talked a lot about this in Math 20, that this doesn't mean, when I write negative x over x, it doesn't mean it's negative. It's in fact going to be positive, isn't it? Because x is a negative number. But this simplifies now to saying the function is equal to 1 whenever x is greater than or equal to 0, and it's equal to -1 if x is less than 0. I want to, in fact, demonstrate that to you by graphing y equals the absolute value of x over x. And I don't know why I feel as though it might help. I'm going to turn off the axes. So I'm going to graph y equals the absolute value of x divided by x. So whenever x is less than 0, the function is equal to -1. I hope you understand I could have graphed each of these separately. I could have graphed y equals -1 with the restriction from -infinity to 0, and then after 0 and including 0, +1. So now we have a visual picture of the graph. And I'm going to answer the question finally by using the graph and then going to the equation, I think. So when I take a look at this graph, this is what it looks like. Does that make sense? This is the absolute value of x over x because it's equal to y equals -1 when x is less than 0, and it's equal to +1 whenever x is greater than or equal to 0. And not that it's a big deal. We like to reserve the or equal to part for the part where we don't need the absolute value sign. Okay. So what were we asked in H? We were asked in H for the limit as x is approaching 0 from the right, I believe. Can you maybe confirm that? Okay. Of the function. So that means we have to be getting closer to 0, but we're doing so on this part of the function that's lying in quadrant 1. And what's happening is we are approaching 1. When we take a look at I, which is the limit as x is approaching 0 from the left of the function, well, from the left of 0, we're over on this part that's in quadrant 3, and as we get closer and closer to 0, y is, quote, approaching -1. Because the left and the right-hand limits are not equal, the answer to j, which is the entire limit, is that it doesn't exist. Now, on the other hand, what you could do, I'm really hesitant in doing this, but I'm going to give it a crack, is you could say, now this is okay, I just have to wrap my head around it, that as we're approaching 0 from the right, we have in our possession a positive value of x. And what that means is that if we have a positive value of x, we don't need to consider the effect of those absolute value signs. So I'm not going to rewrite it because I want to make sure we get enough time today to do stuff. From the right means who cares about the absolute value signs, and it doesn't matter what we put in here, we're going to get 1, right? On the other hand, if I approach 0 from the left, then I have in my possession, I'm putting in a value for x that's a negative number. That's getting closer to 0. Which means that the bottom of this is going to be negative. And the top is going to be the same value as that negative, except it will be positive because of the absolute value. So we can reason out that it's going to become negative 1. Without actually... erase it? I must have erased it. Without actually writing all of that piecewise stuff. Does that help? Okay. And anytime we get to a problem that has an absolute value, basically it turns into two problems. You have to write the piecewise part of the function that's if the argument is greater than or equal to 0, and the piecewise part of the function where the argument is less than 0.